Hello everyone. Today we will study triple integrals in cylindrical coordinates. First of all, let me introduce the cylindrical coordinate system in a three-dimensional space. Let me first introduce the cylindrical coordinate system in a three-dimensional space. In a standard cylindrical coordinate system, every point P in a three-dimensional space can be represented by an ordered triple. R, theta, and z. So in a cylindrical coordinate system, there are three perimeters: R, theta, and z. Here, z represent the distance from point P to the xy plane. Z represents the distance from point P to the xy plane. Let me show you the picture. Assume point P is here. P has three perimeters: R, theta, z. Z represents distance from point P to the xy plane. This distance is distance z here, distance from point P to the xy plane. This distance is z. R and theta represent the polar coordinate of the projection, the polar coordinate of the projection of point P in the xy plane. R and theta represent the projection of point P in the xy plane. This point here is called projection in point. This point here is called projection of point P in the xy plane. Let's call this point Q. So since it's in the xy plane, z coordinate must be 0. Since this point is in the xy plane, the z coordinate must be 0. So point Q is the projection of point P in the xy plane. R is the distance from point Q to the origin. This distance is R. It represents polar coordinate of the projection in the xy plane. So the distance from the projection to the origin is R. Theta is the distance. Let's call this point. Let's call the origin O. Theta is the angle between the positive x-axis and the edge OQ. This is theta. Theta is the angle between the positive x-axis and the edge OQ. So this is called the cylindrical coordinate system. It has three perimeters, r, theta, and z. Z represents distance from point P to the xy plane. R and theta represent the polar coordinate of the projection of P in the xy plane. R and theta represent polar coordinate of the projection in the xy plane. And also keep one thing in mind. Note. In the standard cylindrical coordinate system, R also represent the distance from point P to the z-axis. R also represents the distance from point P to the z-axis. So distance from point P to the z-axis looks like this. Assume if one right angle here. That's distance from point P to the z-axis. Assume if one right angle here. And we know z-axis is perpendicular to the xy plane. Z-axis is perpendicular to the xy plane. It's also perpendicular here. So this is a rectangle. This is a rectangle. The two sides, the opposite side of the rectangle must be the same. So this side is also R. R represents distance from point P to the z-axis. R represents distance from point P to the z-axis. Now, next. Since R and theta represent the polar coordinate of the projection in the xy plane, then we also have x squared plus y squared equal to r squared. Tangent theta equal to y over x. And x equal to r cosine theta. Y equal to r sine theta in general. Since r and theta represent a polar coordinate in the xy plane, y equal to r sine theta. And z is the same as the z in the cylindrical coordinate system is the same as the z in the Cartesian coordinate system. This z in the cylindrical coordinate system is the same as the z in the Cartesian coordinate system. So z is always the same as z. That's the conversion between Cartesian coordinate system and cylindrical coordinate system. That's a conversion between Cartesian coordinate system and cylindrical coordinate system. Next, let's look at some examples. Convert each of the following points from cylindrical coordinate to Cartesian coordinates. Convert each of the following points from cylindrical coordinates to Cartesian coordinates. Look at the first example. Point 1 pi over 6 negative 3 If this point is given to be cylindrical coordinate, then the first component represents r. Second component represents theta. The third component represents z. If we try to convert to Cartesian coordinate, we need to find out x, y, and z. And we know that x is always r cosine theta. Y is always r sine theta. Z stays the same. When we convert from cylindrical coordinate to Cartesian coordinate, x is always r cosine theta. Y is always r sine theta. Z is the same as z. If we plug in, r is 1. Cosine theta, theta is pi over 6. 1 times pi over, cosine pi over 6 is radical 3 over 2. 1 times radical 3 over 2 is radical 3 over 2. Y is r sine theta. R is 1. Theta is pi over 6. We have 1 times sine pi over 6. Sine pi over 6 is half. 1 times half is half. Z is the same as z. Z is negative 3. So the Cartesian coordinate is SYZ. Cartesian coordinate is SYZ, which is radical 3 over 2, comma 1 over 2, comma negative 3. That's the Cartesian coordinate. Another example, 2 pi over 3, comma 1. Convert this point to Cartesian coordinate. If this point is given to be cylindrical coordinate, then the first component represents r. Second component represents theta. Third component represents z. The formula says x is always r cosine theta. Y is always r sine theta. Z is the same as z. If we plug in, r is 2. Theta is 2 pi over 3. Cosine 2 pi over 3. This angle located in quadrant 2. Cosine quadrant 2 is negative. Reference angle is pi over 3. Cosine pi over 3 is a half. 2 times negative half is negative 1. R is 2. Theta is 2 pi over 3. So y is 2 times sine 2 pi over 3. Sine 2 pi over 3. This angle located in quadrant 2. Sine function in quadrant 2 is positive. Reference angle is pi over 3. Sine pi over 3 is a half. Sine function in quadrant 2 is positive. Sorry. Sine pi over 3 is radical 3 over 2. Sine function in quadrant 2 is positive. So if we multiply, number 2 get cancel. We have radical 3 by itself. Z is the same as z. So the Cartesian coordinate here is S, Y, Z equal to negative 1, comma, radical 3, comma, 1. That's the Cartesian coordinate. We convert from cylindrical coordinate to Cartesian coordinate. Next, convert each of the following points from Cartesian coordinate to cylindrical coordinate. First point, 2, negative 2, 4. If this point is given to be Cartesian coordinate, then first component represents x, second component represents y, third component represents z. We try to find the cylindrical coordinate. That means we try to find out r, theta, and z. Since we try to find out the cylindrical coordinate, we try to find out x, y, we try to find out r, theta, and z. The formula says r squared is always s squared plus y squared. R squared is s squared plus y squared. So r squared is 2 squared plus negative 2 squared. 2 squared plus negative 2 squared is 4 plus 4, which is a. So r equal to square root of a. Usually we consider r as positive. Usually we only consider r as positive. Of course, r could be negative, but to make it easier, we only consider positive r. Let r equal to radical a, make it easier. We consider only negative, only positive r, only positive r. Next, for theta, we know that tangent theta is always y equal to x. It's always y over x. Tangent theta is always y over x. And we know y over x is negative 2 over 2. Tangent theta is negative 2 over 2. Negative over 2 is negative 1. And we know this s and y coordinate. S is for this s and y coordinate. X is positive, y is negative. If s is positive, y is negative, this angle theta located in quadrant 4. Since x is positive, y is negative, angle theta located in quadrant 4. Tangent theta is negative 1. Reference angle, the theta bar represents reference angle. Reference angle is pi over 4. Because tangent pi over 4 is 1. So reference angle is pi over 4. Since theta located in quadrant 4, if the reference angle is pi over 4, the theta itself will be 2 pi minus pi over 4. Reference angle is pi over 4. Theta is 2 pi minus pi over 4. Since theta located in quadrant 4, angle is 2 pi minus the reference angle, which is 7 pi over 4. And z coordinate is the same. So the cylindrical coordinate for this point is r theta z equal to 2 radical 2, 7 pi over 4, and z stays the same. Of course, for cylindrical coordinate, since x and y represent polar coordinate, there are more than one representation. But to make it easier, we choose r to be positive. We choose theta belong in the first cycle between 0 and 2 pi. Make it easier. We choose theta to be between 0 and 2 pi in the first cycle. That's a little easier. Next example, we have a Cartesian point, negative radical 3, comma 3, comma negative 1. Convert this point to cylindrical coordinate. If this is Cartesian point, the first component represents x, second component represents y, third component represents z. And using the formula, you can find r squared equal to s squared plus y squared. If we plug in s and y, we have negative radical 3 squared plus 3 squared, which is 3 plus 9 is 12. So r is radical 12. Usually we choose positive r, make it easier. We choose positive r, which is 2 radical 3. Next, we try to find theta. The formula for theta is tangent theta equal to y over x, which means tangent theta is y over x, 3 over negative radical 3, which is negative radical 3. So the reference angle here, the reference angle for theta is pi over 3, because tangent pi over 3 is positive radical 3. Reference angle of theta is pi over 3. Next, let's observe the quadrant. Since x is negative, y is positive. Angle theta located in quadrant 2. Since x is negative, y is positive. Angle theta located in quadrant 2. Since theta located in quadrant 2, reference angle is pi over 3. Theta is pi minus the reference angle. Since theta located in quadrant 2, and we know the reference angle, theta is pi minus the reference angle. Pi minus pi over 3 is 2 pi over 3. Usually we choose pi to be in the first cycle between 0 and 2 pi, make it a little easier. Choose r to be greater than 0, choose theta to be between 0 and 2 pi in the first cycle. It's a little easier. So the cylindrical point, the cylindrical coordinate r theta z, r is 2 radical 3. Theta is 2 pi over 3. Z stays the same. Z is negative 1. That's the cylindrical coordinate. That's the cylindrical coordinate for this point. Both of them represent the same point. This is Cartesian coordinate. This is cylindrical coordinate. In general, to make it easier for cylindrical coordinate, we choose r to be positive. We choose theta to be between 0 and 2 pi. Next example. Draw a surface represented by each of the following equations. Draw a surface represented by each of the following given equations. First equation, theta equal to pi over 3. Let's draw a surface represented by this equation, theta equal to pi over 3. What kind of graph it is? If z coordinate is missing, if the z coordinate is missing, let's try to draw the projection in the xy plane first. If the z coordinate is missing, let's try to draw the projection in the xy plane first. We're going to try to draw a surface. If the z coordinate is missing, let's draw the projection in the xy plane first. How do we draw theta equal to pi over 3 in the xy plane? In the xy plane, theta is pi over 3. That means angle start from positive x-axis is pi over 3. And r is missing. That means r could be 0, r could be 1, r could be 2, r could be 3. It's the entire line here. And also r could be negative 1, negative 2, negative 3. R could be negative 1, negative 2, negative 3. So that's the entire straight line. This is the projection of theta equal to pi over 3 in the xy plane. Now, since z is missing, since z component is missing, z could be 1, 2, 3, 4, 5. Z could be negative 1, negative 2, negative 3, negative 4, 5. So So that's the plane. That's the plane. We draw the projection in the xy plane first. Then since z could be positive negative, we draw a plane above this line, perpendicular to the xy plane. We draw a plane above this line, and perpendicular to the xy plane. This plane represents this equation, theta equal to pi over 3. Next example, r equal to 2. Similarly, if z component is missing, we try to draw the projection in the xy plane first. Since z component is missing, we try to draw the projection in the xy plane first. R is 2. R represents the radius of a circle. That means distance from the point to the origin is 2. In the xy plane, the distance from the origin to the point is 2. It represents an entire circle. The distance from a point to an origin is 2. Theta is missing, could be any angle. So that's the entire circle. When theta is 0, we are here. When theta is pi over 3, when theta is pi over 6, pi over 3, pi over 2. We have an entire circle here. So that's a circle, that's a projection in the xy plane. Since z coordinate is missing, z could be 1, 2, 3, 4, 5, the circle may go up, and z could be -1, -2, the circle may go down. So it's a cylinder. Since z is missing, the graph is a cylinder. So the graph is cylinder. That's the projection in the xy plane. It's a cylinder. Z may be positive, Z may be negative. It's a cylinder. That's the graph. This surface here represent. This surface represent the equation r equal to 2. It goes through 2 in the x-axis and 2 in the y-axis. This cylinder represents this equation. Next. Z equal to r squared. The equation z equal to r squared, theta is missing. If theta is missing, we try to draw the picture. If theta is missing, we try to draw the picture in the xz plane, yz plane, then rotate the picture. If theta is missing, try to draw the graph in the xz plane and yz plane. Then make notation. In xz plane, y coordinate is 0. In xz plane, y coordinate is 0. So in the xz plane, y coordinate is 0. So r squared is the same as, since r squared is s squared plus y squared. In the xz plane, y coordinate is 0. So r squared equal to s squared. In xz plane, we have z equal to r squared. Let's draw the picture let's draw intersection in the xz plane first. It's a parabola. Now, in the yz plane, s coordinate is 0. In the yz plane, s coordinate is 0. So we have r squared equal to y squared. We sketch the graph z equal to y squared. In the yz plane, s coordinate is 0. So we have r squared equal to y squared. So z equal to y squared in the yz plane. The cross section in the yz plane is z equal to y squared. It's also a parabola. That's when theta equal to 0. That's what happens when theta equal to pi over 2. Then theta could be 3 pi over 2, 2 pi. Let's rotate a cycle here. If I rotate these two surfaces, that's the cross section in the xz plane. This is a cross section in the yz plane. If I rotate these two surfaces, I have an elliptic paraboloid. If we notate the cross section, we have an elliptic paraboloid. If we rotate the cross section, that's an elliptic paraboloid. And this surface represents the equation z equal to r squared. This surface represents the equation z equal to r squared. Next example, z equal to 2r. In this equation, we can see that the theta is missing. If theta is missing, we try to graph the cross section in the xz plane and yz plane. Then rotate the cross section, we can get a graph. We know that r squared equal to s squared plus y squared. In the xz plane, y component must be 0. In the xz plane, y component must be 0. If y component is 0, we have r squared equal to s squared. So r equal to plus minus x. So this equation z equal to 2r can be rewritten as z equal to plus minus 2x. So that's a line that slope is positive 2 and negative 2. That's a line that slope is positive 2 and negative 2. When the slope is positive 2, it looks like this. That's a line when the slope is positive 2, z equal to 2x. When z equal to negative 2x, that's a line beside this. So that's the cross section in the xz plane. This is a cross section in the xz plane. But the thing is, when I rotate this cross section, this piece will cover the other piece. This piece will cover the other piece. If we rotate this piece 180 degrees, it will cover this piece here. So we only need half of the graph. We only need half of the graph for rotation. If we rotate, this piece will eventually cover this piece here. So we only need half of the graph. That's the cross section in positive xz plane. That's the cross section in xz plane. Now, the cross section in yz plane. The cross section in yz plane, s coordinate must be 0. So we have z equal to plus minus 2y. That's the cross section in yz plane. When we rotate, we can see that it forms a circle. When we rotate the cross section, we can see that it forms a circle. That's the upper half of the circle. That's an upper half of the circle. That's an upper half. It looks like a cone. It looks like a cone. That's an upper half of the graph. It looks like a cone. And for the lower half, it's very similar. That's an upper half of the graph. It looks like a cone. The lower half is very similar. That's the lower half of the cone. That's the lower half of the cone. So that's the graph for the equation z equal to 2r. That's the graph for the equation z equal to 2r. Now, for the first 4 equations, are we able to tell the graph without drawing it out? For the first 4 examples, are we able to tell the graph without actually sketch the graph? Are we able to tell what kind of graph it is? Let's observe the first equation. Theta equal to pi over 3. Since z is missing, let's draw the cross section in the SY plane first. How's the graph in the SY plane looks like? We have theta equal to pi over 3. If we apply tension to both sides, Tangent theta will be tangent of pi over 3. And we know that tangent theta, there's a formula that says tangent theta is y over x. If we replace tangent theta with y over x, we have that y over x equal to tangent pi over 3. Tangent pi over 3 is radical 3. If I multiply both sides by x, I have y equal to radical 3x. So we can see that that's a straight line in the xy plane. Since g component is missing, the graph is a plane passing through y equal to radical 3x in the xy plane and perpendicular to the xy plane. The graph is a plane passing through the line y equal to radical 3x in the xy plane and perpendicular to the xy plane. For the second example, I will be able to tell what kind of graph it is. For the second example here, we have r equal to 2. I will be able to tell the graph what kind of graph it is. For this equation, we can also see that the g component is missing. We can graph the cross section in the xy plane first. What kind of cross section do we have in the xy plane? We have r equal to 2. That means r squared equal to 4. And we know that r squared is x squared plus y squared equal to 4. That's a circle. That's a circle in the xy plane with radius 2. That's a circle in the xy plane, center and origin with radius 2. Then since g is missing, the graph is a cylinder passing through this circle perpendicular to the xy plane. So that's the simplified equation. Here we write the equation in Cartesian coordinate. That's a little easier to sketch the graph. Write the equation in Cartesian form. That's a little easier to sketch the graph. And third example, g equal to r squared. I will be able to tell what kind of graph it is without actually draw it out. We have g equal to r squared. We know that r squared is x squared plus y squared. And we can see that this is an elliptic paraboloid. This is an elliptic paraboloid, open upward. This is an elliptic paraboloid. So if we convert polar equation to Cartesian equation, we can recognize the graph a little easier. For number 4, what can we do here? Can we recognize what kind of graph it is? We have g equal to 2r squared. G equal to 2r. If I square both sides, I have g squared equal to 4r squared. And we know that r squared is x squared plus y squared. G can be rewritten as 4x squared plus 4y squared. And this equation is a cone. This equation is a cone. This is a cone. So by changing polar equation to Cartesian equation, that's a little easier to recognize what kind of graph it is. By changing the polar equation to Cartesian equation, it's a little easier to recognize what kind of graph it is. I mean, polar equation, I mean cylindrical coordinate. Polar equation, I mean cylindrical coordinate. Next example. R equal to 2 sine theta. I'll be able to tell what kind of graph it is. R equal to 2 sine theta. So let's try to change this equation to Cartesian equation. This is in cylindrical form. Let's try to change this cylindrical equation to Cartesian equation. If I multiply both sides by r, I can make r squared equal to 2r sine theta. R squared is x squared plus y squared. R sine theta is y. Then if I move everything over and complete square, we have x squared plus y squared minus 2y equal to 0. If I complete square, I can make y squared minus 2y. I can add 1 to both sides. That can be rewritten as x squared plus y minus 1 equal to 1. That's a circle in 2D, that's a circle in the xy plane, center at 0, 1 with radius 1. And since z is missing, the graph is a cylinder passing through this circle perpendicular to the xy plane. So the graph looks like this. It's a circle, center at 0, -1, 0, 1. It's a circle centered at 0, 1 in xy plane. Then if we consider this as a 3D graph, it's a cylinder perpendicular to xy plane passing through the circle. That's the graph. It's a circle. In 2D graph, it's a circle centered at 0, 1 with radius 1. As a 3D graph, the graph is a cylinder perpendicular to the xy plane and passing through the circle. That's how the graph looks like. So in general, if we change polar equation or cylindrical equation into Cartesian equations, we can recognize the picture a little easier. If we change polar equation or cylindrical equation into Cartesian equation, we can recognize the graph a little easier. Next example, r equal to 1 plus sine theta. In this equation, you can see that the z component is missing. So we can try to find the cross section in the xy plane first. If the z component is missing, we can try to find the cross section in the xy plane first. To find a graph in the xy plane, we can try to convert this equation to Cartesian equation. But we can see that this equation is very hard to convert to Cartesian equation. Since it's very hard to convert to Cartesian equation, let's graph the line by plotting points. Since this is very hard to convert to Cartesian equation, we sketch the curve by plotting points. In the xy plane, the intersection is a curve. We sketch the curve by plotting points. When theta is 0, sine 0 is 0, 1 plus 0 is 1. When theta is pi over 2, sine pi over 2 is 1, 1 plus 1 is 2. When theta is pi, sine pi is 0, 1 plus 0 is 1. When theta is 3 pi over 2, sine 3 pi over 2 is 1. Sine 3 pi over 2 is negative 1. Negative 1 plus 1 is 0. When theta is 2 pi, sine 2 pi is 0. 0 plus 1 is 1. Let's sketch the graph in the SY plane. When theta is 0, r is 1. When theta is pi over 2, r is 2. When theta is pi, r is 1. When theta is 3 pi over 2, r is 0. When theta is 2 pi, r is 1. Then we can connect the point, make a graph. Usually you connect 3 points at a time. Try to use smooth curve. Connect 3 points at a time. Use smooth curve, connect 3 points. Then use smooth curve, connect 3 points. Use smooth curve, connect 3 points. Use smooth curve, connect 3 points. Looks like a heart shape. Looks like a heart shape in the SY plane. It looks like a heart shape in the SY plane. Then we try to sketch this graph in the 3D plane. In the 3-dimensional SY plane. Let's put this graph in the 3-dimensional SY plane. That's the heart shape in the 3-dimensional SY plane. Then we try to draw a cylindrical shape passing through this curve and perpendicular to the SY plane. This surface represents the equation. This surface represents the equation. This surface represents this equation. Next example. Draw a solid that satisfies all given conditions. Draw a solid that satisfies all given conditions. First example, theta is between pi over 6 and pi over 3. R is between 0 and 2. G is between 0 and 3. Draw a solid that satisfies all these conditions. So usually if possible, let's draw the cross section in the xy plane first. If possible, let's draw the cross section in the xy plane first. For the cross section in the xy plane here, theta is between pi over 3 and pi over 6. Pi over 3 and pi over 6. Assume that's positive x-axis, that's positive y-axis. This is 0 degree, 90 degree, pi over 6 is 30 degree, pi over 3 is 60 degree. Assume this angle here is pi over 6 and this angle here is pi over 3. Then R is between 0 and 2. R is between 0 and 2. Radius 0 is here in the origin. Radius 2 looks like this. Radius from 0 to 2. Assume this distance is 2. So that's the cross section in the xy plane. That's the cross section in the xy plane. And G is between 0 and 3. So G goes from 0 to 3. Looks like a birthday cake. Looks like a birthday cake. It looks like a birthday cake. This solid satisfies all these three inequalities. Theta between pi over 3 and pi over 6 and pi over 3. R is from 0 to 2. Z is from 0 to 3. The graph looks like a birthday cake. Next example. Theta between 0 and pi over 2. Z is between 2r and 4, and 2r is greater than 0. Sketch the graph. Draw the solid that satisfies all this inequality. Here, when theta is 0, the graph is in the xz plane. When theta is 0, we have the cross section in the xz plane. When theta is pi over 2, we have the cross section in the yz plane. So let's try to graph the intersection in the xz plane and yz plane first. Let's draw the cross section in the xz plane and yz plane first. Since z is greater than 0, we only have the image above the xy plane. Since z is positive, we only have the region above. We only have the solid above xy plane. So when theta is 0, we have cross section in the xz plane. When theta is pi over 2, we have cross section in the yz plane. Let's draw the cross section in xz plane first. Z is greater than 2r and less than 4. Z equal to 2r in the xz plane. In the xz plane, y coordinate is 0. We have z equal to 2x, because r squared equal to s squared plus y squared. If y squared is 0 and r is positive, then r must equal to x. That's the cross section in the xz plane. In the yz plane, we have z equal to 2y. That's the cross section in the xz plane, in the yz plane. Then rotate the graph. Rotate the angle theta from 0 to pi over 2. That's when theta is 0. Here is when theta is pi over 2. Rotate 90 degrees. That's the solid when I rotate 90 degrees. Theta from 0 to pi over 2. That's a quarter of a cone. That's a quarter of a cone. This is quarter of a cone. Next, let me introduce triple integrals in cylindrical coordinates. We know that single integral represents area under the curve over an interval. Double integral represents the volume under the surface over a region. And the triple integral represents the total mass of a solid if we treat the function f of s, y, z as a density function over the solid region. For triple integrals in cylindrical coordinates, let's look at the following example. Let f of r theta z be a positive function. Let B be the set of points r theta z in R3, where R is between A and B. Theta is between alpha and beta, and Z is between C and D. Let B be a let B be a cylindrical box. A cylindrical box looks like this. R is between A and B. That's a cylindrical box. R is between A and B. Theta is between alpha and beta. Theta is between alpha and beta. Z is between C and D. Let's call a cylindrical box. R is between A and B. Theta is between alpha and beta. Z is between C and D. Let's call a cylindrical box. Let B be a cylindrical box. Suppose the function f of r theta z is continuous on B. Find the triple integral f of r theta z over the rectangular box B by finding the total mass of B if we treat the function f of r theta z as a density function. As the density function over B. In order to find the total mass, I first of all divide the cylindrical box B. This is box B. I first of all divide the cylindrical box B into small boxes. So I first of all divide the interval AB into n subintervals. R sub 0, R sub 1, R sub 2, R sub I minus 1, R sub I. The second last one is R sub n minus 1. The last one is R sub n. I first of all divide interval AB into n subintervals. Let's take our typical one. Let's take our typical interval. A typical subinterval is from Ri minus 1 to Ri. Let's pick a typical subinterval. Let's pick a typical subinterval from Ri minus 1 to Ri. If I take out this piece, that's one shear of cylindrical box. This is one shear of this cylindrical box. If we take out this piece, that's one shear of this cylindrical box. It looks like this. That's one shell of this cylindrical box. Ri minus 1 is here. This is Ri. So the width of this shell is delta Ri. The width of the shell is delta Ri. This is Ri minus 1. This is Ri. The width of the shell is delta Ri. Next, I divide the angle delta from alpha to beta into m subintervals. I divide the angle theta from alpha to beta into m subintervals. I divide interval into m subintervals. So alpha will be theta 0. Theta 1, theta 2. In general, in the middle, we have theta j minus 1, theta j. Last one, beta will be theta m. So we have m subintervals here. We have m subintervals. Theta 0, theta 1, theta 2. In the middle, a typical one would be theta j minus 1, theta j. Those are the partitions. Then we have m subinterval here. Let's take our typical one. Called the jth one. The one in the middle, the jth one. Let me take out this one in the middle. There are m subintervals. Let's take our typical strip here. Looks like there are m substrips. Let's take out one typical strip called the jth one. A typical strip, the jth one. If I take out this typical strip, it looks like this. That's a typical strip in the middle, where here the width of this strip is delta Ri. Ri minus 1 is here, Ri is here. Angle here. The angle here is theta m, theta j minus 1. And theta j is here. So the angle between this, the angle is delta theta j in the middle. Angle in the middle is delta theta j. Next, we divide the interval CD into k subintervals. I divide interval CD into k subintervals. So C is here, D is here. C is here, D is here in the z-axis. C is here, D is here. I divide interval CD into k subintervals. So C is Z0, Z1 is here, Z2 is here. In general, in the middle, we have Z sub L minus 1, Z sub L. Let me say Z sub k, ijk. Let's say Z sub k here. I divide interval CD into M, into L subintervals. Z sub k minus 1, Z sub k. Last one is ZL. First one is Z0. Z1, Z2, Z sub k minus 1, Z sub k. Last one is ZL. Let me take out a typical one. We divide this strip into L L little boxes. I divide this strip into L sub little boxes. Let me take out a typical one. There are arrow sub-boxes. I take our typical one from middle. I take our typical one between Z sub k minus 1 and Z sub k. I take our typical one between Z sub k and Z sub k minus 1. Take our typical one here. If I take our typical one, I put it here. If I take our typical boxes, it looks like this. So in this typical box, the width here is delta Ri. The angle here, angle in the middle, the angle in the middle is delta theta j, and the height of the box, the height of the box is, the height is between g sub k minus 1 and g sub k. That's delta g sub k. That's the dimension of this box. That's the dimension of this little box. Next, inside the box. Next, inside the box, let me draw the box here. That's the box. Let me draw the box completed here. That's the box. So next, inside the box, we pick sample point. We try to approximate the mass. We try to find the mass of the box. So I pick sample point to approximate the density of the box. Inside the box, I pick sample point. Inside the box, I pick sample point. It could be anywhere inside the box, could be anywhere inside. Pick sample point in the middle. Let's call this point Ri star theta j star g sub k star. It could be anywhere inside the box. Let's call this sample point Ri star theta j star g sub k star. Pick sample point. They use the sample point to approximate the volume of the box. Use the sample point to approximate the density of the box. We know that the mass of a box, the mass of the box is density times volume. Since we use the point Ri star, theta j star, and g sub k star to approximate the density, since f represents density function, I use the sample point Ri star, theta j star, g sub k star represent to approximate the density. Then density times the volume. Density times the volume of this box. Take density times the volume of the box. That's the mass of the box. The volume of the box is Vijk. That's the volume of the box, Vijk. That's the mass. That's the mass of one box here. That's the mass of one box here. Next, since I pick typical box on the strip, if I find a sum L from 0, take the sum K from 0 to L. If I find a sum that K goes from 0 to L. If I find a sum that K goes from 0 to L, I find the sum of the entire strip here. Next, since this is a typical strip inside this shell, if I take the sum that J goes from 0 to M, if I take the sum that J goes from 0 to M, J from 0, 1, 2, 3 up to M. If I take the sum that J goes from 0 to M, I find the total mass of this entire shell. I find the total mass of the entire shell. If I take J from 0 to M, I find the total mass of the entire shell. Next, this is a typical shell of this solid. If I take I from 0 to N, I find the total mass of this entire cylindrical box. If I find the sum that I goes from 1 to N, I from 0 to N, it should be 1. They all start from 1. 1 to N, 1 to M, 1 to L. I find the sum of the entire cylindrical box. This is the sum. This is the sum of one shield. This is the mass of one shield. If I find the sum for every shield together, I find the total mass of the entire cylindrical box. So that's the approximate mass of the cylindrical box B. Now, if we try to find the actual mass of the cylindrical box, we must take a limit. Take a limit as the maximum delta Ri approach to 0, maximum delta theta j approach to 0, maximum delta z sub k approach to 0. If we take a limit here, as the maximum delta I approach to 0, maximum delta theta j approach to 0, and maximum delta z sub k approach to 0, this cylindrical box will be very, very small. This cylindrical box will be very, very small. So after this limit, we will find the actual mass of the cylindrical box. So this limit will give you the actual mass of the cylindrical box, which is the triple integral f of r theta z dv over the cylindrical box B. Next, let's try to compute delta V of ijk. That's the volume of the cylindrical box. That's the volume of the little cylindrical box. That's the volume of this cylindrical box. So when delta Ri, delta theta j, delta zk become very, very small, this box will be very, very close to a rectangular box. This cylindrical box will be very, very close to a rectangular box. When each side become very, very small, if we zoom in, make the box become very, very small, it will be approximately a rectangular box. So for rectangular box, the volume is length times width times height. For rectangular box, the volume is length times width times height. Let's find the length, width, and height first. The length is this arc. The length is this arc here. The width is delta xi. The width is delta si. Sorry, delta ri. The width is delta ri. The height is delta zk. How do we find the length of this arc? This is circular arc. The length of circular arc is the central angle times the radius. Usually it's r theta. Central angle times the radius. The length of a circular arc is the central angle times the radius. Central angle times radius. What's the central angle here? For this arc, for this length of arc, we can see that the central angle is delta theta j. The central angle is delta theta j. The central angle is delta theta j. How about the length of an arc? Remember, how about the radius? Central angle is delta theta j. How about the radius? Central angle is delta theta j. The radius, if we use this arc and that arc, radius is different. If we use this arc and this arc here, radius is different. This arc here is r. This arc is ri minus 1. For this arc, the radius is ri minus 1. For this arc, the radius is ri. They are not the same. So in order to find the radius, we try to use the sample point. Try to use the radius from the sample point. Sample point is here. We try to use Ri star here. We try to use Ri star to approximate the radius. We try to use Ri star to approximate the radius of this arc. So we use Ri star to approximate the radius of this arc, of this circular arc. So that's the length, that's the width, that's the height. Volume of a rectangular box is length times width times height. If we multiply length times width times height, it's So the volume of this rectangular box WV of ijk is length times width times height, which is Ri star times delta Ri times delta theta j times delta zk. If we multiply out length times width times height, I have Ri star delta xi delta theta j delta zk. That's the volume of this cylindrical box. That's the volume of this cylindrical box. So here we know that delta Vijk, delta V sub ijk it can be rewritten as Ri star times delta Ri times delta theta j times delta zk. If I plug in delta sub ijk into this formula, we have the triple integral f of r theta z over the cylindrical box B equal to the limit maximum delta Ri approach to 0, maximum delta theta j approach to 0, maximum delta z sub k approach to 0. I from 1 to n, j from 1 to m, k from 1 to l. F of Ri star theta j star zk star times delta Ri star times Ri star times delta Ri times delta theta j times delta zk. Now, if I let the function g of r theta z equal to f of r theta z times the extra r here, then g of Ri star theta I star z g of Ri star theta j star z sub k star will be the same as f of Ri star theta j star z sub k star times Ri star. If there's extra r, that's what I have here. Then, if I plug in g here, if I plug in g for function f, so I have if I plug in g for f, so the triple integral f of r theta z dv equal to the limit maximum delta Ri approach to 0, maximum delta theta j approach to 0, maximum delta z sub k approach to 0, sum of I from 1 to n, j from 1 to m, k from 1 to l. Function f will be f of Ri star theta j star z sub k star times Ri star. This part will be g of Ri star theta j star z sub k star. times delta Ri delta theta j delta z sub k. If we substitute function g here, that's what I get here. Then by Fubini's theorem, this limit can be rewritten as integral theta from alpha to beta, r from a to b, g from c to d. That's the dimension of the cylindrical box B. R between A and B, theta between alpha and beta, g between c and d. Function g of r theta g. Now match the order here. We have dg, dr, d theta. Next, I can replace function g with function f times r. I can replace function g with function f, r theta g times r. I can replace function g with function f times r. dg, dr, d theta stays the same. This is the triple integral. F of r theta g over the cylindrical box B. This is the triple integral in cylindrical coordinates. This is the triple integral in cylindrical coordinates. This is the triple integral in cylindrical coordinates. Now, what if f is a function of s, y, z? What if f is a function of s, y, z? Over the same cylindrical box B. What if f is a function of s, y, z over the cylindrical box B? First of all, we can change x and y in terms of, we can rewrite x and y in terms of I and theta. Let's change x and y first. Write both x and y in terms of I and theta. S can be rewritten as r cosine theta. Y can be rewritten as r sine theta. Z stays the same. So this is a function of r theta z. Then use the formula here. We have theta from alpha to beta, r from a to b, g from c to d. Function f stays the same. R cosine theta, r sine theta, z. There's extra r here. R, dg, dr, d theta. That's how we change a triple integral from Cartesian coordinate to cylindrical coordinate. That's how we change a triple integral from Cartesian coordinate to cylindrical coordinate. Let me rewrite everything over. Change from Cartesian to cylindrical coordinate. In a triple integral. Let B be the set of points R theta z belong to R3. That's three-dimensional space where R must be positive between A and B. Theta is between alpha and beta, with beta minus alpha is greater than 0, is between 0 and 2 pi. The difference between alpha and beta is between 0 and 2 pi, with beta minus alpha between 0 and 2 pi. And Z is between C and D. Let B be a cylindrical box with points R, theta, Z in R3, where R is between A and B, and R must be positive. Theta is between alpha and beta. Beta minus alpha must be between 0 and 2 pi. And Z is between C and D. Let B be a cylindrical box. Suppose F is continuous on B. Then the triple integral f of SYZ over the cylindrical box B is the triple integral theta from alpha to beta, R from A to B, Z from C to D, f of R cosine theta, R sine theta Z, there's extra R here, dz, dr, d theta. That's how we change from Cartesian to cylindrical coordinates in a triple integral. So keep in mind that in a triple integral, when we change from Cartesian to cylindrical coordinate, we first of all rewrite x and y in terms of r and theta. First of all, write x and y in terms of r and theta. Then replace dv with r, dz, dr, d theta. Replace dv with r, dz, dr, d theta. Keep in mind that dv always equal to r, dz, dr, d theta. That's how we change coordinates in a triple integral over a cylindrical box B. That's how we change coordinates in a triple integral over a cylindrical box B. In general, we can also change coordinates for triple integral over a type 1 solid. In general, we can also change the coordinates for triple integral over a type 1 solid, type 2 solid, and type 3 solid. We can also change coordinates for triple integral over type 1, type 2, and type 3 solid. Next, let me show you everything in detail. For type 1 solid, let me call the solid E. For type 1 solid E, it's a cylindrical solid bounded by a lower surface and upper surface. Lower surface z equal to u1 of sy, upper surface z equal to u2 of sy. And let D be its projection in the xy plane. Let D be its projection in the xy plane. Then I can write solid E in the following way. Let E be the set of points SYZ in R3, where X and Y belong to D, and Z is between U1 of SY and U2 of SY. Where D is the projection of E in the xy plane. Assume f of syz is continuous on E. Then the triple integral f of syz over solid E can be rewritten as, by Fubini's theorem, it can be rewritten as double integral over region D. That's an outer integral. In the integral, we take integral from lower surface to upper surface. F of syz dz dA. That's the triple integral in Cartesian coordinates. If we change from Cartesian coordinates to cylindrical coordinates, look at the projection D first. Look at the projection D first. For solid E, for type 1 solid E, projection D is a region in the xy plane. The projection D is in a region in the xy plane. In the xy plane, if we apply polar coordinate in the xy plane, x is always r cosine theta, y is r sine theta. So I can first of all write x and y in terms of r and theta. If I write x and y in terms of r and theta, double integral stays the same. The inner integral is z equal to u1 r cosine theta, r sine theta, like x and y in terms of r and theta. Z equal to u2 r cosine theta, r sine theta. F of r cosine theta, r sine theta. Z stays the same. dz dA. That's how we change from Cartesian coordinate to cylindrical coordinates over a type 1 solid. That's how we change from Cartesian coordinate to cylindrical coordinate over a type 1 solid. For type 2 solid, let's also call the solid E. Type 2 solid looks like this. It's a cylindrical solid. Its projection is a region in the xc plane. That's a type 2 solid. For type 2 solid, let E equal to the point of syz in R3, where xz, point xz belongs to D, and y is between u1 of sz, that's the left side surface, u2 of xz, that's the right side surface, u1 of sy, u1 of sc is the left side surface, u2 of sc is the right side surface. It's type 2 solid, where D is the projection of E in the xc plane. D is the projection of E in the xc plane. D is the projection of E in the xc plane. Assume f of syz is continuous on E, then by Fubini's theorem, the triple integral can be rewritten. By Fubini's theorem, the triple integral can be rewritten as a double integral over the region D in the xz plane. Y is from lower surface, from left side surface to right side surface. F of syz dz dA. This is the triple integral in Cartesian coordinates. If we try to change to cylindrical coordinates, look at region D first. D is a region in the xz plane. So in xz plane, if we convert to polar coordinate, if we convert a point in xz plane to polar coordinates, x is the same as r cosine theta. Now here, z actually represents y. So z is actually r sine theta. In xz plane, if we convert the points to polar coordinates, x is the same as x r cosine theta. Z here actually represents y in the xy plane. This z represents y in the xy plane. So z will be r sine theta. So if D is a region for type 2 solid, if the projection D is a region in the xz plane, we convert all points in xz plane to polar coordinates, then S will be r cosine theta, Z will be r sine theta. So this integral can be rewritten as double integral D. We write x and z in terms of r and theta. In terms of r and theta. So y is u1 r cosine theta. Z is r sine theta. So write u1 xz in terms of r and theta. X is r cosine theta. Z is r sine theta. Same thing in the upper limit. Y equal to u2 r cosine theta, comma r sine theta. Write x and z in terms of x and y. Now here, be very, very careful. Leave y in the same. It should be dy here. Sorry. Y must match this. It must be dy here. Leave y in the same. Write x as r cosine theta. Leave y in the same. Write z as r sine theta. Dy, dA. Here, write x as r cosine theta. Write z as r sine theta. Leave y in the same. That's a different type of cylindrical coordinates. R, theta, y. We apply polar coordinates for all points in the xz plane. Apply polar coordinates for all points in the xz plane. F is a function of r, theta, y. We write all points in the xz plane in polar coordinates. For type 3 solid, let's also call the solid E. E is a solid perpendicular to YZ plane. E is a cylindrical solid perpendicular to the YZ plane. And the projection of E is D in the YZ plane. Projection of E is a region D in the YZ plane. That's called type 3 solid. For type 3 solid E, let E be the set of points SYZ let E be the set of points S, Y, Z in R3. Where YZ belongs to D, where for every point, the YZ coordinate belongs to region D in the YZ plane. And X is bounded by a back surface U1 of YZ and a front surface U2 of YZ. X is bounded by a back surface U1 of YZ and a front surface U2 of YZ, where D is the projection of E, where D is a projection of E in the YZ plane. D is a projection of E in the YZ plane. Assume f of SYZ is continuous on E. Then by Fubini's theorem, the three-point integral can be rewritten as double integral over region D in the YZ plane. Double integral over region D in the YZ plane. The inner integral, x is from the back surface, x equal to U1 of YZ to the front surface, s equal to U2 of YZ. F of SYZ dx dA. That's the three-point integral in Cartesian coordinates. If we try to change the three-point integral to cylindrical coordinates, look at region D first. D is a region in the YZ plane. That means we need to apply polar coordinates for all points in the YZ plane. If we apply polar coordinates for points in YZ plane, this Y actually represents the x-axis in the SY plane. This Z actually represents the y-axis in the SY plane. So Y can be rewritten as R cosine theta. Z can be rewritten as R sine theta. In the YZ plane, this y-axis here actually represents the s-axis in the SY plane. This z-axis actually represents the y-axis in the SY plane. So Y is R cosine theta, Z is R sine theta. If we apply polar coordinate for all points in the YZ plane. So if we try to change from Cartesian coordinate to cylindrical coordinates, rewrite each YZ in terms of R and theta, rewrite Y and Z in terms of R and theta. If we try to convert Cartesian coordinate to cylindrical coordinates, rewrite Y and Z in terms of R and theta. So the lower bound x is U1 R cosine theta, Z is R sine theta, Y is R cosine theta, Z is R sine theta. So upper limit U2, Y is R cosine theta, Z is R sine theta. Then keep x the same. Don't touch x, keep x the same. Write Y as in terms of R and theta. Y is R cosine theta. Write Z in terms of R and theta. Z is R sine theta. Dx dA. So that's how we convert from Cartesian coordinate to cylindrical coordinate. That's how we convert from Cartesian coordinate to cylindrical coordinate over a type 3 solid E. Based on the triple integral over these three types of solids, we can see that there are actually three different types of cylindrical coordinates. So keep in mind that in general, there are three types of cylindrical coordinates. Type 1 cylindrical coordinate has three perimeters, r, theta, z. For the first type, we keep z the same, keep z coordinate the same, and we change x and y coordinates to polar coordinates. S equal to r cosine theta, y equal to r sine theta. We keep z coordinate the same, change x and y coordinate to polar coordinates in the xy plane. For type 2 cylindrical coordinates, we have three perimeters, r, theta, and y. We keep y coordinate the same. Keep y coordinate the same. For points in the SC plane, there are three perimeters, r, theta, and y. For points in the SC plane, we change x and z. We change x and z coordinate to polar coordinates. Change s and z coordinate to polar coordinates. So s equal to r cosine theta, z equal to r sine theta. Type 3. There are three perimeters, r, theta, and x. There are three perimeters, r, theta, and x. We keep s coordinate the same. Change y and z coordinate to polar coordinates. Change y and z coordinate to polar coordinates. For all points in the yz plane, change y to r cosine theta, z to r sine theta. Keep s coordinate the same. Change yz coordinate to polar coordinates. Y equal to r cosine theta, z equal to r sine theta. The first type is called the standard cylindrical coordinates. The first type is called the standard cylindrical coordinate. If the problem doesn't specify which type of cylindrical coordinate, we assume it's the first type. That's the most common type. If the problem doesn't specify which type, we assume it's always the first type, the standard cylindrical coordinates. So for type 1 solid, if we try to take triple integral using cylindrical coordinates, we must use the type 1 cylindrical coordinates, which has three perimeters, r, theta, z. We keep z coordinate the same, then change x and y coordinates to polar coordinates. For type 2 solid, if we try to use cylindrical coordinates to take triple integrals, we must use type 2 cylindrical coordinates, in which we keep y coordinate the same. And write x and z in terms of r and theta. Change x and z to polar coordinates. Here x represents x in xy coordinate. Z represents y in the xy coordinates. So s equal to r cosine theta, z equal to r sine theta. Keep y coordinate the same. Change x and z to polar coordinates. For type 2 solid, if we try to take triple integral using cylindrical coordinates, we must use type 3 cylindrical coordinates, which means we have three coordinates. We have three perimeters, r, theta, and x. in which we keep S coordinate the same. Change YZ coordinate to polar coordinates. So here, Y represent X in the SY plane. Z represent Y in the SY plane. So Y equal to R cosine theta. Z equal to R sine theta. That's how we take triple integrals for these three types of solids. Also, keep in mind that there are three different types of cylindrical coordinates. The first type is called the standard cylindrical coordinates. In general, when people talk about cylindrical coordinates, if they don't specify which type, we assume they're talking about the first type, the standard cylindrical coordinates. But when we solve a problem, sometimes we need to choose the right type cylindrical coordinates to solve a problem. In general, for type 1 solid, we choose the type 1 cylindrical coordinates. For type 2 solid, we choose the type 2 cylindrical coordinates. For type 3 solid, we choose the type 3 cylindrical coordinates. Next, let's look at some examples about triple integrals of Sy over the solid region E, where E is the set of R theta Z in R3, where R is between 0 and 3, theta is between 0 and pi over 2, and Z is between 0 and 2R. So let's set out the integral first. By Fubini's theorem, this integral can be rewritten as the inner integral Z is from 0 to 2R. R is from 0 to 3. Theta is from 0 to pi over 2. Xy dv here is for cylindrical coordinates. Be very careful. dv is always r dz dr d theta. For standard cylindrical coordinate, dv is always r dz dr d theta. R dz dr d theta. And we must write x and y. In terms of r and theta. If we write s and y in terms of r and theta, x is r cosine theta, y is r sine theta. Then if we multiply out, we have the triple integral theta from 0 to pi over 2, r from 0 to 3, z from 0 to 2r. This integral can be rewritten as r to the power 3 cosine theta sine theta dz dr d theta. Then we solve the innermost integrals. Leave the outer integral the same. Theta from 0 to pi over 2. R is from 0 to 3. Solve the inner integral. We're taking antiderivative with respect to z. That means we treat r and theta as constants. We have r to the power 3 cosine theta sine theta times z. Z is from 0 to 2r. dr d theta. Then we plug in 2r and 0 for z and subtract. Theta from 0 to pi over 2. R from 0 to 3. If we plug in 2r for z, 2r times r cubed is 2r to the power 4. Cosine theta, sine theta, dr d theta. Now here we see that we can write the function, we can write the integrand as a product of function of r times a function of theta. And all the boundaries are constants. Here I can separate this integral into two integrals. I can separate this double integral into two single integrals. R is from 0 to 3. Let me take r to the power 4. I leave number 2 to be part of the theta function. theta is from 0 to pi over 2. If I leave number 2 together with the theta function, 2 sine theta cosine theta, use double angle formula. 2 sine theta cosine theta is sine 2 theta. If I leave number 2 together with sine and cosine, 2 sine theta times cosine theta is sine 2 theta. Then take antiderivative for each of them. We have r to the power 5 over 5. R from 0 to 3. The other one, take antiderivative for sine. I have negative cosine of 2 theta times a half. Evaluate from 0 to pi over 2. If I plug in 3, I have 243 over 5. If I plug in 0, I get 0. If I plug in pi over 2, cosine pi over 2. Cosine pi over 2 times 2 is cosine pi. Cosine pi is negative 1. If I substitute 0, cosine 0 is 1. So this part here is a half. Half plus a half is 1. So the final answer is 243 over 5. Next example, evaluate the triple integral of S cubed over the solid region E, where E is the point of the set of points r theta z in R3, where r is between 0 and radical 3, theta is between 0 and 2 pi, and z is between 0 and 3 minus r squared. So let's set out the integral first. Theta is from 0 to 2 pi. R is from 0 to radical 3. Z is from 0 to 3 minus r squared. The function is S cubed. We need to write S cubed in terms of, we need to write x in terms of r and theta. Here, S can be rewritten as r cosine theta, and with power 3 outside. S cubed is r cosine theta cube, and dv for cylindrical coordinates. For standard cylindrical coordinates, dv is always r dz dr d theta. Then solve the integral from inner to outer. Let me simplify first. Theta is from 0 to 2 pi. R is from 0 to radical 3. Z is from 0 to 3 minus r squared. If we multiply out, we have r to the power 4, cosine to the power 3 theta, dz, dr, d theta. Then we solve the innermost integral first. The innermost integral. Take antiderivative with respect to z. Take antiderivative with respect to z. We have r to the power 4 cosine to the power 3 theta times z, where z is from 0 to 3 minus r squared, dr d theta. Then substitute the upper and lower limit. If we substitute the upper limit, we have r to the power 4 cosine to the power 3 theta. If I substitute the upper limit, z is 3 minus r squared dr d theta. If we substitute lower limit, we get 0. Now we can see that here, I can write the integral as a function of r and function of theta. I can write the integral as a product of function of r times function of theta, and all the limits are constants. So I can separate this double integral into two single integrals. R is from 0 to 2 pi. Sorry, theta is from 0 to 2 pi. Function of theta is cosine cube theta d theta. Function of r is from 0 to radical 3. Function of r is r to the power 4 times 3 minus r squared dr. Then here we have two single integrals. Solve each of them individually, then multiply back. First integral, it can be rewritten as 0 to 2 pi cosine squared theta times cosine theta d theta. Cosine squared theta can be rewritten as 1 minus sine squared theta cosine theta d theta. Then here we can do u substitution. The u will be sine theta. The u will be cosine theta d theta. If we substitute, we have 1 minus u squared times du. If we substitute 0, we get 0. Substitute 2 pi, we get 0. This integral is 0. Integral from 0 to 0 is 0. And since we get 0 in the first integral, no matter what the second integral is, answer is always 0. Since we get 0 from the first integral, no matter what we get from the second integral, answer is always 0. So the answer for this integral is 0. Next, evaluate the triple integral of g over the solid region E, where E is a solid region enclosed by the paraboloid g equal to x squared plus y squared, and the plane g equal to 4. So let's draw the solid region E first. E is bounded by the paraboloid and the plane g equal to 4. That's the paraboloid. G equal to x squared plus y squared. That's the paraboloid. And the plane g equal to 4 is a plane that going through 4 in the z-axis. That's the plane g equal to 4. So you can see that this is a type 1 solid. The projection of this solid region in the xy plane is a circle. Projection of this solid region in the xy plane is this circle. Projection of this solid in the xy plane is this circle here. From top to bottom, all you can see is this circle. So the projection in the xy plane is a circle. Upper surface is equal to 4. Lower surface is equal to x squared plus y squared. So let's set out the integral. In the integral, g is from x squared plus y squared to g equal to 4. Integrand is g dg. The outer integral is double integral over region D, dA, where D is a projection in the xy plane. D is this circle in the xy plane. From top to bottom, all you can see is this circle, and that's the projection in the xy plane. So the projection in the xy plane is a circle. Now, usually when we see a circular region, when we see a circular region, we try to set out a circular region using polar coordinates. When we see a circular region, we try to set out a circular region using polar coordinates. What's the radius of this circle? What's the radius of this circle? This circle here is the same as this circle. This circle, the projection in the xy plane is the same as this circle. This circle is the intersection of the plane g equal to 4 and the paraboloid g equal to x squared plus y squared. So this circle must satisfy both equations. If we set this equation equal to each other, we have x squared plus y squared equal to 4. If we set this equation equal to each other, we have x squared plus y squared equal to 4. That's a circle of radius 2. So r is from 0 to 2. This is a circle of radius 2. It's a full cycle. This circle is a full cycle. Theta goes from 0 to 2 pi. G is from x squared plus y squared to 4. G dg. And dA, for polar coordinate, dA is r dr d theta. Usually we bring r inside. Usually to make it easier, bring r inside. So we have the integral theta from 0 to 2 pi, r from 0 to 2. We write, since we are using cylindrical coordinates, change r and x and y in terms of x and y in terms of r and theta. X squared plus y squared is always r squared. So lower limit is c equal to r squared. X squared plus y squared in polar coordinates is always r squared. Since we're using cylindrical coordinates, we write x and y in terms of r and theta. Bring r inside, we have g times r, dg, dr, d theta. Then solve the integral from inner to outer. Take antiderivative with respect to g. We have half of g squared times r. G is from r squared to 4. dr d theta. Then plug in 4, plug in r squared. If we plug in 4, 4 squared is 16. 16 times half is 8. We get AR. If we substitute r squared for g, we have r squared squared, that's r to the power 4. R to the power 4 times r, that's r to the power 5. We get half r to the power 5 dr d theta. Here we can write the integral as a function of r times function of theta. Function of theta is 1. So I can write this double integral as a product of two single integrals. R is from 0 to 2 pi. Integral is 1 times d theta. Theta is from 0, r is from 0 to 2. Integral is AR minus half of r to the power 5 dr. Then take antiderivative. Antiderivative of 1 is theta from 0 to 2 pi. Antiderivative of AR is 4r squared. Antiderivative of half of r to the power 5 is 1 over 12 r to the power 6. Evaluate from 0 to 2. If we solve the first integral, we get 2 pi. Solve the second integral, if we plug in 2. 2 squared is 4. 4 times 4 is 16. If we plug in 2 here, 2 to the power 6 is 64. 64 over 12 is 16 over 3. If we plug in 0, we get 0. 16 minus 16 over 3 is 32 over 3 times 2 pi. The final answer is 64 over 3 pi. Next example, evaluate the triple integral of x over the solid region E, where E is a solid region between two cylinders, x squared plus y squared equal to 4, and x squared plus y squared equal to 9, and bounded by the planes g equal to 0 and g equal to s plus y plus 5. Let's draw the solid region first, if possible. Let's draw the solid region first. This solid region is bounded by between two cylinders, x squared plus y squared equal to 4 and x squared plus y squared equal to 9. That's a cylinder radius 2. That's a cylinder of radius 3. We're looking for the solid region between two cylinders, bounded by the plane s equal to 0 and s equal to g, and g equal to 0 and g equal to s plus y plus 5. G equal to 0 is an SY plane. G equal to 0 is an SY plane. G equal to s plus y plus 5 is this plane here. Is this plane here. So lower plane, lower surface is g equal to 0. Upper surface is g equal to x plus y plus 5. The projection in the SY plane. The projection in the SY plane is a region between two circles. That's the projection in the SY plane. If you look at the picture from top to bottom, that's the projection of this solid. It's a region between two circles. From top to bottom, that's the projection in the SY plane. That's the region between two circles. That's the projection in the SY plane. So that's region D. This is a type 1 solid. This is a type 1 solid. I set out integral this way. And D is the projection in the SY plane. D is a projection in the XY plane. And for region D, R is from 2 to 3. These two circles, radius is from 2 to 3. It's a full cycle, so theta is from 0 to 2 pi. Z is from 0 to S plus Y plus phi. X dz. And dA for polar coordinate, dA is R, dr, d theta. In general, we can bring R inside. Theta is from 0 to 2 pi. R is from 2 to 3. Z is from 0 to S plus Y plus phi. And since D is a region in the XY plane, we must write X and Y in terms of I and theta. Since D is a region in the XY plane, we must write X and Y in terms of I and theta. So X and Y, we must write it in terms of I and theta. X is R cosine theta. Y is R sine theta. Leave number 4 in the same. And this X is R cosine theta. And since I bring this X inside, since I bring this R inside, R times R will be R squared dz dr d theta. Then we solve from the inner integral first. Theta is from 0 to 2 pi. R is from 2 to 3. Take antiderivative with respect to z. We have R squared cosine theta times z. Z is from 0 to R cosine theta plus R sine theta plus 5 dr d theta. Then we substitute z. Let's check. Theta is from 0 to 2 pi. R is from 2 to 3. R squared cosine theta. If I substitute the upper limit, we have R cosine theta plus R sine theta plus 5 dr d theta. If I substitute 0, I get 0. Then let's integral from theta from 0 to 2 pi. R from 2 to 3. Let me simplify this first. I distribute R squared theta. I distribute R squared cosine theta. I have R to the power 3 cosine squared theta plus R to the power 3 cosine theta sine theta plus 5R squared cosine theta dr d theta. Then take antiderivative with respect to R. Theta from 0 to 2 pi. Take antiderivative with respect to R. I have R to the power 4 over 4 cosine squared theta plus R to the power 4 R to the power 4 over 4 cosine theta sine theta plus 5R to the power 3 over 3 cosine theta. Evaluate R from 2 to 3 d theta. Then plug in 3 and 2 and take difference. If we plug in 3 3 to the power 4 is 81. If we plug in 3 here, 3 to the power 4 is 81. If we plug in 3 here, 3 squared is 27. 27 divided by 3 is 9. 9 times 5 is 45. cosine theta. If we substitute 2, 2 to the power 4 is 16, 16 over 4 is 4. If we substitute 2 here, 2 to the power 4 is 16, 16 over 4 is 4. If we substitute 2 here, 2 to the power 3 is 8. 8 times 4 is 40. We get 40 over 3. Cosine theta, d theta. Then combine like terms. Integral from 0 to 2 pi. If we combine like terms, 81 over 4 minus 4. I can write 4 as 16 over 4. And subtract 81 minus 16 is 65 over 4. 65 over 4 cosine square theta. Same thing, another 81 over 4 minus 4 is 65 over 4 cosine theta sine theta. 45 minus 40 over 3. I have 95 over 3. Then next, take antiderivative with respect to theta. Take antiderivative with respect to theta. Let me simplify first. Cosine square, if I use double angle formula, it can be written as half of 1 plus cosine 2 theta. Cosine theta times sine theta, if we use double angle formula, it can be rewritten as half of sine 2 theta plus 95 over 3 cosine theta d theta. If we multiply out, it can be rewritten as 65 over 8, 1 plus cosine 2 theta plus 65 over 8 sine 2 theta plus 95 over 3 cosine theta d theta. Then take an antiderivative. We have 65 over 8. Antiderivative of 1 is theta. Antiderivative of cosine 2 theta is half of sine 2 theta. Antiderivative of sine 2 theta is negative half of cosine 2 theta. Antiderivative of cosine theta is sine theta. Evaluate from 0 to 2 pi. If we substitute 2 pi, we have 65 over 8, 2 pi plus, if I substitute 2 pi here, I have 2 times 2 pi is 4 pi, sine 4 pi is 0. If I substitute 2 pi here, cosine 4 pi is 1. If I substitute 2 pi here, sine 2 pi is 0. If I substitute 0, theta is 0, sine 0 is 0. Cosine 0 is 1. Cosine of 0 is 1. We have 65 over 8 times negative half. Sine 0 is 0. Simplify, we have 65 over 4 times pi plus minus 65 over 4 minus minus is plus 65 over 4 plus 0. So the answer is 65 over 4 pi. Next, evaluate the triple integral of y over solid region E, where E is a solid region inside the cylinder x squared plus y x squared plus z squared equal to 1, and bounded by the xz plane and the plane y plus z equal to 6. Let's first of all draw the solid region first. E is a solid region inside the cylinder x squared plus z squared equal to 1. One component is missing. This cylinder is parallel to the y-axis. This cylinder is parallel to the y-axis. This cylinder is parallel to the y-axis and bounded by the xz plane. xz plane is here, bounded by xz plane, and the plane y plus z equal to 6. In this equation, x component is missing. So the graph is a plane. That passing through the line y plus z equal to 6 in the yz plane. The graph is a plane that perpendicular to the yz plane. The graph is a plane perpendicular to the yz plane and passing through the line. Y plus z equal to 6 in the yz plane. The graph of this is a plane perpendicular to the yz plane and passing through the line y plus z equal to 6. So the intersection looks like this. When a plane cuts through a cylinder, the intersection is an ellipse. When a plane cuts through a cylinder, intersection is an ellipse. That's the plane y plus z equal to 6. This plane here is the xz plane, which is the plane y equal to 0. And that's the solid region E. And here we can see that this solid region is a type 2 solid. This is a type 2 solid. We can clearly see that there's a left side surface, right side surface, and the projection is a circle. Projection is a circle in the xz plane. This is a type 2 solid. For type 2 solid, we try to write y in terms of x and z. For type 2 solid, we try to write y in terms of x and z. For these two planes, try to write y in terms of x and z. This plane already have y by itself. This plane y plus z equal to 6, it can be rewritten as y equal to 6 minus z. So that's the lower surface, that's an upper surface. Y is from 0 to 6 minus z. Left surface is a lower limit. Right side surface is an upper limit. Integrand is y dy. That's the inner integral. The outer is a double integral over region D. The outer integral is a double integral over region D, where D is the projection in the yz plane. D is the projection in the xz plane. if you look at the picture this way, from right to left, you can see that the projection in SC plane is this circle. That's a circle of radius 1. So projection in the SC plane is a circle of radius 1. That's region D in the SC plane. That's region D in the SC plane. When we see a circular region, we try to apply polar coordinates. When we see a circular region, try to apply polar coordinates in SC plane. So in SC plane, X represent X in the SY plane. Z represent Y in the SY plane. Z is R sine theta. Z represent Y in the SY plane. So X is R cosine theta. Z is R sine theta. So set up the integral. R is a full cycle. R is from 0 to 2 pi. Radius is 1. Radius is 1. So theta is from 0 to 2 pi. Radius is 1. R is from 0 to 1. Theta is from 0 to 2 pi. Y is 0. I write here for the inner integral, write X and Z in terms of R and theta. Write S and Z in terms of R and theta. Z is R sine theta. Y stays the same. dy stays the same. dA is, for polar coordinate, dA is always R dr d theta. R dr d theta. Then try to bring R inside. Bring R inside. Make it a little easier. Bring R inside. Theta from 0 to 2 pi. R from 0 to 1. Y from 0 to 6 minus R sine theta. Bring R inside. Ry. dy, dr, d theta. We solve the inner integral first. Solve the inner integral first. Take antiderivative with respect to y. We have half of ry squared, where y is from 0 to 6 minus r sine theta. dr d theta. Then substitute upper and lower limit, take difference. If I substitute the upper limit, I have half r 6 minus r sine theta squared. If I substitute the lower limit, I get 0. dr d theta. Then simplify. Theta from 0 to 2 pi. R is from 0 to 1. Half of r. 30, expand perfect square, I get 36 minus 12r sine theta plus r squared sine squared theta. dr d theta. Distribute half of r. Theta is from 0 to 2 pi. R is from 0 to 1. We have 18r minus 6r squared sine theta plus half of r cubed sine squared theta. dr d theta. Then take antiderivative with respect to r. Theta is from 0 to 2 pi. take antiderivative with respect to r. We have 9r squared minus 2r cubed sine theta plus 1 over 8 r to the power 4 sine squared theta. Evaluate from 0 to 1. If we substitute 1, if we substitute 1 here, we have 9 minus 2 sine theta plus 1 over 8 sine squared theta. If I substitute 0, I get 0. Next, take antiderivative with respect to theta. Here, for sine squared theta, let's apply half angle identity first. Next, take antiderivative with respect to theta. We have 9 theta minus 2 negative cosine theta plus 1 over 16. Antiderivative of 1 is theta. Antiderivative of cosine is sine. So for cosine 2 theta, I get sine 2 theta, half of sine 2 theta. Evaluate from 0 to 2 pi. If I substitute 2 pi, I have 18 pi minus double negative is positive. 2 times cosine of 2 pi. Cosine of 2 pi is 1. If I substitute 2 pi here, I have 2 pi minus sine 2 pi. Sine 4 pi is 0. If I substitute 0, 9 times 0 is 0. Cosine 0 is 1. Cosine 0 is 1. I have positive 2 here. Plus, for the last term, if I plug in 0, 0 is 0. Sine 0 is also 0. Last term is 0. So I have 18 pi plus 2 plus 1 over 16 times 2 pi is 1 over 8 pi minus 2. So plus 2 minus 2 can cancel. We have 18 pi minus 1 over 8 pi, which is 18 pi plus 1 over 8 pi, which is 144 pi plus 1 over 8 pi, which is 145 pi. 145 pi over 8. That's the final answer. Next, evaluate the integral. Outer integral is from negative 2 to 2. Middle integral is from negative radical 4 minus s squared to radical 4 minus s squared. Inner integral is from s squared plus y squared to 4. Integrand is x. Then we have dz, dy, dx. So if we try to solve this integral directly, you can see that it's very hard. If you try to solve it directly, you can try. This integral is very, very hard if you try to solve it directly. So another way to solve it is we try to draw the solid first, draw the solid region first, then set our integral in a different way. If we try to solve it directly, you can try. It cannot be very, very hard. So another way to solve it is we try to draw the solid region first, then set up the integral in a different way. Let's draw the solid region first. Let's draw the solid region first. Here we can see that lower bound is z equal to s squared plus y squared. Upper bound is z equal to 4. And the lower surface is a paraboloid, it's an elliptic paraboloid. Upper surface is a plane. Lower surface is the elliptic paraboloid. Upper surface is the plane z equal to 4. That's an upper surface. That's a lower surface. Now, the projection in the xy plane. What's the projection in the xy plane? From top to bottom, all we can see is this circle. This is the projection in xy plane is this circle. Projection in xy plane is this circle. Projection in xy plane is this circle. All we can see from top to bottom is this circle here. That's the projection in the xy plane. And this circle is the intersection of these two equations. This circle is the intersection of these two circles. So it satisfies both equations. This equation here, this circle here, is the intersection of both graphs. So it must satisfy both equations. If we substitute, we have 4 equal to x squared plus y squared. So the projection in the xy plane is a circle. X squared plus y squared equal to 4. That's the projection in the xy plane. X squared plus y squared equal to 4. And projection including everything inside the circle. The boundary is the equation x squared plus y squared equal to 4. It must satisfy both equations. Z equal to x squared plus y squared and z equal to 4. So we have x squared plus y squared equal to 4. That's the projection in the xy plane. Now let's look at the y bound. Y, lower bound for y is negative radical 4 minus x squared. Upper bound for y is radical 4 minus x squared. If I square both sides, y squared equal to 4 minus x squared. So x squared plus y squared equal to 4. Same thing for the top one. Also we have x squared plus y squared equal to 4. So the upper bound represents the upper half of this circle. Upper bound represents the upper half of this circle. Lower bound represents the lower half of this circle. This circle has radius from negative 2 to 2. This circle has radius from negative 2 to 2. And here, outer limit says x is from negative 2 to 2. So x is from negative 2 to 2. It actually represents the entire circle here. This limit, this s bound and y bound together represent the entire circle here. Since the s bound and y bound represent the entire circle, which is the projection in the xy plane, so the solid region is everything above this projection between the two surfaces. And this is a type 1. This is a type 1 surface. We can see that this is a type 1 surface. So keep z coordinate the same. Lower surface is x squared plus y squared. Upper surface is z equal to 4. Projection is this circle. When we see a circular region, apply polar coordinates. When we see a circular region, apply polar coordinates. That's the inner integral. Outer integral is a double integral over region D, dA. And when we see a circular region, apply polar coordinates. This is circle radius is from 0 to 2. Theta is a full cycle. Theta is from 0 to 2 pi. Z is x squared plus y squared. We write x and y in terms of r and theta. So x squared plus y squared is r squared. Upper bound is equal to 4. This x is r cosine theta. In xy plane, x is r cosine theta. dz. dA is r dr d theta. dA is r dr d theta. Then we multiply r inside, make it a little easier. Multiply this r inside. Theta from 0 to 2 pi. R from 0 to 2. G from r squared to 4. If I multiply r inside, I have r squared cosine theta dg dr d theta. Take antiderivative with respect to g first. Theta is from 0 to 2 pi. R is from 0 to 2. If I take antiderivative with respect to g, I have r squared cosine theta times g. Evaluate g from r squared to 4 dr d theta. Then substitute upper and lower limit and take difference. If I substitute 4, I have 4r squared cosine theta. If I substitute r squared, I have r to the power 4 cosine theta. dr d theta. Then I can factor, I can pull out cosine theta. I can factor, pull out cosine theta. If I pull out cosine theta, I have cosine theta times 4r squared plus r to the power 4 dr d theta. Now here I write the integrand as a function of r times function of theta. I write integrand as a function of r times function of theta. Then, since the limits are constants, I can separate this double integral into two single integrals. Theta from 0 to 2 pi, cosine theta d theta. R is from 0 to 2, 4r squared plus r to the power 4 dr. Take antiderivative with respect to theta. I have sine theta from 0 to 2 pi. If I substitute 2 pi, I get 0. If I substitute 0, I also get 0. So this integral is 0. 0 times everything. 0 times everything is 0. 0 times everything, no matter what it is here. 0 times everything is 0. Since the first integral is 0, it doesn't matter what the second integral is. 0 times 0. 0 times everything is 0. So that's the final answer. Next example, outer integral from 0 to 2. Middle integral from 0 to radical 4 minus s squared. Inner integral from 0 to radical 16 minus s squared minus y squared. The integrand is radical s squared plus y squared. dz, dy, dx. If we try to solve this integral directly, it's very hard. There are too many square roots. If we try to solve the integral directly, it's very, very hard. So, in this situation, we try to draw the solid region first, then set a different integral based on the solid region. Let's draw the solid region first, then set a different integral based on the solid region. For the solid region, inner integral is g. Lower bound is g equal to 0. Upper bound is g equal to 16 minus upper bound is g equal to radical 16 minus s squared minus y squared. So lower bound g equals 0 is in the xy plane. G equals 0 is in the xy plane. Upper bound g equal to radical 16 minus s squared minus y squared. If I square both sides, I can make g squared equal to 16 minus s squared minus y squared. If I move s squared, y squared over, I have s squared plus y squared plus g squared equal to 16. That's a sphere of radius 4. This is a sphere of radius 4. Since lower bound is g equals 0, it's a hemisphere. It's the upper half hemisphere of radius 4. The graph is the upper half hemisphere of radius 4. So it's a upper half hemisphere of radius 4. The projection in the xy plane is this circle. It's the equator. The projection in the xy plane is the equator. It's the equator of the sphere. The projection in the xy plane is the equator of the sphere. So which is a circle. How big the circle is. Projection is a circle in the xy plane. But how big the circle is. How big the circle is. In xy plane, in the xy plane, the z coordinate is 0. If I substitute 0 for z coordinate, if I substitute 0 for z coordinate, I have x squared plus y squared equal to 16. So it's a circle of radius 4. Projection in the xy plane is a circle of radius 4. Projection in the xy plane is a circle of radius 4. Now, let's look at the y bound. Y is from 0 to radical 4 minus x squared. Y equals 0. In the xy plane, y equals 0 is an x-axis. Upper bound, y equal to radical 4 minus x squared. If I square both sides, y squared equal to 4 minus x squared. X squared plus y squared equal to 4. That's a circle of radius 2. So, lower bound is y equals 0. Upper bound is the semicircle. Of radius 2. Center and origin of radius 2. That's lower bound, that's upper bound. X is from 0 to 2. So that's a quarter of a circle. Region D, the projection, region D is a quarter of a circle of center and origin of radius 2. So the projection of this solid is a circle in the xy plane of radius 2. Center and origin with radius 2. So we don't have the entire hemisphere. For solid region E, we don't have the entire hemisphere because the projection is this circle, not the entire circle. Projection is this quarter of a circle. It's not the entire circle. So the solid region E is not the entire hemisphere. Because the projection is smaller, it's not an entire circle here. So let me draw this region over. It's a region below the hemisphere, above this region D. The solid region is the solid below the hemisphere, above the solid region D. That's the solid region. Upper surface is a hemisphere. Z equal to radical 16 minus x squared minus y squared. Lower surface is an xy plane. Z equal to 0. Projection is region D. Region D is a quarter of a circle. Center and origin with radius 2. So that's the solid region. That's the solid region. We can see that this is a type 1 solid. This is a type 1 solid. So we keep the Z bound the same. Lower surface is 0. Upper surface is a hemisphere. Radical x squared plus y squared dz. That's an inner integral. Then for the outer integral, we take a double integral over region D, dA. For the outer integral, we take a double integral over region D, dA. And region D is a quarter of a circle of radius 2. So theta is from 0 to pi over 2. Since it's a quarter of a circle, theta is from 0 to pi over 2. Radius is 2, so r is from 0 to 2. Since D is a region in the xy plane, I try to write x and y in terms of r and theta. Since D is a region in the xy plane, we try to write x and y in terms of r and theta. Theta is from 0 to pi over 2. R is from 0 to 2. Z is from 0 to 16 minus, we try to write x and y in terms of r and theta. X squared plus y squared is r squared. X squared plus y squared is r squared. We have radical r squared, which is r. Radical r squared is r. dz. dA is r dr d theta. dA is always r dr d theta if we use polar coordinates. dA is always r dr d theta. Then we bring this r inside. Theta from 0 to pi over 2. R is from 0 to 2. Z is from 0 to radical 16 minus r squared. Bring r inside, we have r squared. dz, dr, d theta. Then take antiderivative with respect to z. We have r squared z. Z is from 0 to radical 16 minus r squared. dr d theta. If I substitute an upper and lower limit, I have integral theta from 0 to pi over 2. R from 0 to 2. If I substitute an upper limit, I have r squared radical 16 minus r squared dr d theta. If I substitute lower limit, I got 0. Then the integrand is a function of r. That means I can run the function as a function. I can run the integrand as a function of r times function of theta. And since the limits are constants, I can separate it into two single integrals. Theta is from 0 to pi over 2. 1 d theta times r from 0 to 2. R from 0 to 2. R squared radical 16 minus r squared dr. First integral is simple. Take antiderivative for 1, I get theta. Theta from 0 to pi over 2. That's pi over 2. First integral is pi over 2. Second integral is harder. Second integral, we need to apply trig substitution. This is not straightforward. We need to apply trig substitutions. Second integral from 0 to 2. R squared radical 16 minus r squared dr. Apply trig substitution. Let r equal to 4 sine theta. R over 4 equal to sine theta. Draw a triangle. Theta, sine theta is opposite over hypotenuse. Use Pythagorean theorem for the missing sign. We have 16 minus r squared. Next, find the relationship between radical and constant. That's adjacent, that's opposite. Adjacent over opposite is cosine. cosine theta equal to adjacent over opposite. Multiply both sides by 4. 4 cosine theta is radical 16 minus r squared. So if we substitute here, r is 4 sine theta. R squared is 4 sine theta squared. Radical 16 minus r squared is 4 cosine theta. For dr, we can take derivative for r. Take derivative for r with respect to theta, we have 4 cosine theta d theta. So we have 4 cosine theta d theta. That can be written as integral of 4 squared is 16. 16 times another 16 is 256. Sine squared, cosine squared. That can be rewritten as sine theta cosine theta squared d theta. Sine squared, cosine squared together is sine theta cosine theta squared. And the limit here, if I substitute 2 for r, sine theta is a half. If I substitute 2 for r, sine theta is a half. And we know sine pi over 6 is half. So upper bound is pi over 6. If I substitute 0, I get sine theta equal to 0. We know sine 0 is 0, so theta must be 0. So it's from 0 to pi over 6. Next, let's take integrals here. Sine squared, cosine squared, if I use double angle formula, that can be rewritten as half of sine 2 theta squared. Sine times cosine, sine theta times cosine theta. If I use double angle formula, that's half of sine 2 theta. Then square each of them. Half square is a quarter. Quarter times 256 is 64. Sine squared 2 theta d theta. Next, for sine squared 2 theta, apply half angle identity. That's half of 1 minus cosine 4 theta d theta. 64 times half is 32. I can bring it outside. 1 minus cosine 4 theta d theta. Next, take antiderivative with respect to theta. I have theta minus 1 over 4 sine 4 theta. Evaluate theta from 0 to pi over 6. If I substitute pi over 6, I have pi over 6 minus a quarter sine 4 times pi over 6 is 2 pi over 3. If I substitute 0, I get 0. Next, simplify this. Sine 3 pi over 2. 3 pi over 2 is the angle in quadrant 2. Sine function is positive in quadrant 2. Reference angle of 2 pi over 3 is pi over 3. Sine pi over 3 is radical 3 over 2. So the answer is 32 times pi over 6 minus radical 3 over a. 32 times pi over 6 minus radical 3 over a. So if we solve this integral, we have 32 times pi over 6 minus radical 3 over a. If we multiply these two answers, we have 16 pi over 6 minus radical 3 over a. 16 pi times pi over 6 minus radical 3 over a. If we solve it this way, it's easier than solving this integral directly. Even though it's still hard, but it's much easier than solving these two integrals, solving these integrals with these two square roots. Next example, outer integral from -1 to 1. Middle integral from 0 to radical 1 minus y squared. Inner integral from 0 to x. The integrand is x squared plus y squared. dg dx dy. If we try to solve this integral directly, you can try. Eventually, you will see it's very hard to get an answer at the end. There's a square root here. So if we try to solve it, it's very hard to be solved. In this situation, we try to draw the solid region first, then set out the integral in a different way based on the solid region. Let's draw the solid region first. The inner integral is dg. Lower bound is g equal to 0. Upper bound is g equal to x. G equal to 0 is the xy plane. G equal to 0 is the xy plane. G equal to x. G equal to x. Y component is missing. So let's draw g equal to x. Let's draw g equal to x in the xz plane first. Let's try to draw g equal to x in the xz plane first. That's the line g equal to x in the xz plane. Then since y component is missing, the graph is a plane. The graph is a plane perpendicular to the line g equal to x, and the graph is a line perpendicular to the xz plane and passing through the line g equal to x. This plane represents g equal to x, and g equal to 0 is the xy plane. Now next, let's try to find a projection based on s and y coordinate. Let's try to find a projection. We know projection is in the xy plane. X is from 0 to radical 1 minus y squared. So s equals 0, that's the left bound. S equals 0, the lower limit is the left bound. In the xy plane, s equals 0 is the y-axis, so that's the left bound. Right bound is s equal to the radical 1 minus y squared. If I square both sides, s squared equal to 1 minus y squared. That means s squared plus y squared equal to 1. So the right bound is a circle. It's a semicircle. It's a right half semicircle. Right half semicircle with radius 1. That's left bound. That's the right bound. And y is from -1 to 1. Y is from -1 to 1. That's the lower bound. That's the upper bound. That's the solid region D. This is the solid region D. It's a right half semicircle. It's a right half semicircle in the xy plane. That's the projection in the xy plane. That's the projection in the xy plane. So the intersection looks like this. The region below the plane above region D looks like this. The region below the plane above region D looks like this. That's a solid region below the plane g equal to x. There's a solid region below the plane g equal to x, above the solid region, above the region D. D is this semicircle here. So this is a type 1 solid. This is a type 1 solid. G is from 0 to x. That's the inner integral. Outer integral is the double integral over region D. Then for region D, it's a semicircle center and origin with radius 1. So theta is from, here is from negative pi over 2 to pi over 2. Theta is from negative pi over 2 to pi over 2. Theta is from negative pi over 2 to pi over 2. In order to make integral passive, we must integrate counterclockwise. In order to make integral passive, we need to integrate counterclockwise. Theta from negative pi over 2 to pi over 2. For theta, we always integrate counterclockwise. For theta, always integrate counterclockwise. R is from 0 to 1. G is from 0 to x. X squared plus y squared, we can write it in terms of r and theta. So I first of all write this x in terms of r and theta. X is r cosine theta. X squared plus y squared is r squared. dg stays the same. dA is, in polar coordinate, dA is always r, dr, d theta. In polar coordinates, dA is always r, dr, d theta. Next, we first of all bring r inside. Make it easier, bring r inside. Theta from negative pi over 2 to pi over 2. R from 0 to 1. G from 0 to r cosine theta. Bring r inside. We have r to the power 3, dg, dr, d theta. Then we solve the inner integral first. Work from inner to outer. Theta from negative pi over 2 to pi over 2. R from 0 to 1. If we take antiderivative with respect to g, we have r to the power 3 times z. G from 0 to r cosine theta. dr, d theta. Then we substitute the upper limit and lower limit. If we substitute lower limit, we get 0. So all we need is substitute the upper limit. So we have theta from negative pi over 2 to pi over 2. R from 0 to 1. If I substitute upper limit, we have r to the power 4 cosine theta dr, d theta. Then the integral, I can write it as a product of function r times function of theta. And the limits are constants, so I can separate this double integral into two single integrals. Theta is from negative pi over 2 to pi over 2. Cosine theta d theta. R is from 0 to 1. R to the power 4 dr. Then take antiderivative for each of them. Antiderivative of cosine theta is sine theta. Evaluate from negative pi over 2 to pi over 2. Antiderivative of r to the power 4 is r to the power 5 over 5. Evaluate from 0 to 1. If we substitute pi over 2, sine pi over 2 is 1. Sine negative pi over 2 is negative 1. If we substitute 1 here, I get 1/5. If we substitute 0, we get 0. That's 2 times 1/5, which is 2/5. So solve it using double integral is easier than solve the integral directly. If it's too hard to solve it directly, we can draw a solid region, then set up the integral in a different way based on the solid region. Next, find the volume of the solid inside the cylinder s squared plus y squared equal to 1, bounded by the paraboloid z equal to s squared plus y squared and z equal to s squared plus y squared plus 1. So the volume of a solid, the formula is always the triple integral of 1 over the solid region E. That's how we find the volume of a solid. So in order to take an integral, we must draw the solid region first. Let's draw solid region first. The solid region is a region inside a cylinder. Cylinder s squared plus y squared equal to 1. That's a cylinder parallel to the z-axis. That's a cylinder of radius 1 parallel to the z-axis. That's cylinder of radius 1 parallel to the z-axis. Bounded by the paraboloid z equal to s squared plus y squared and z equal to s squared plus y squared plus 1. That's a lower paraboloid. The vertex is the origin. The vertex is the origin. That's the lower paraboloid. The upper paraboloid vertex is 1 on the z-axis. Its vertex is 1 in the z-axis. We're looking for the solid region inside the cylinder between these two paraboloid cylinders, between these two paraboloid. We're looking for the solid region between these two paraboloid. So here we can see that the upper surface, this is a type 1 region, this is a type 1 solid. This is a type 1 solid. Lower bound is z equal to s squared plus y squared. Upper bound is z equal to s squared plus y squared plus 1. Lower limit is the lower paraboloid. Upper limit is the upper paraboloid. Integral is 1 dz. Then we take double integral over d. D is the projection in the xy plane. Projection in the xy plane is this circle here. Projection in the xy plane is this circle here. This is a circle of radius 1. This is a circle of radius 1. This is a circle of radius 1. This is a circle of radius 1 in the xy plane. This is a circle of radius 1 in the xy plane. So when we see a circular region, we apply polar coordinate in the xy plane. So r is from 0 to 1. Theta is from 0 to pi over 2. r is from 0 to 1, theta is from 0 to pi over 2. For z, for the integral, we try to write x and y in terms of r and theta. For the integral, try to write x and y in terms of r and theta. So for z equal to x squared plus y squared, that's r squared. For the upper bound, z equal to x squared plus y squared plus 1, that's r squared plus 1. Number 1 stays the same, dz stays the same. For polar coordinate, dA is r dr d theta. Then this integral can be rewritten as theta from 0 to pi over 2. 0 to 2 pi is a full cycle, sorry. Theta is from 0 to 2 pi is a full cycle. R is from 0 to 1. Bring r inside. Z is from r squared to r squared plus 1. R dz dr d theta. Take inner integral first. Take inner integral first. We have r z. Z is from r squared to r squared plus 1. dr d theta. Substitute the upper limit and lower limit and take a difference. We have r times r squared plus 1 minus r times r squared dr d theta. This is r cubed times r cubed plus r minus r cubed dr d theta. Cancel r cubed. Theta is from 0 to 2 pi. R is from 0 to 1. R dr d theta. Then the integrand, I can write it as a product of function of r times function of theta. And all the limits are constant, so I can write this double integral as a product of two single integrals. Theta from 0 to 2 pi. Function of theta is 1. R is from 0 to 1. Function of r is r itself. Take antiderivative for 1, I get theta. Evaluate from 0 to 2 pi, I get 2 pi. Take antiderivative for r. Let me put it here. Take antiderivative for 1, I get theta. Evaluate from 0 to 2 pi. Take antiderivative for r, I get r squared over 2. Evaluate from 0 to 1. For the first integral, if I plug in 2 pi, I get 2 pi. If I substitute 0, I get 0. So 2 pi minus 0 is 2 pi. For the second integral, if I substitute 1, I get a half. If I substitute 0, I get 0. So the answer is 2 pi times half is pi. That's the volume of this solid. Next, find the volume of the solid bounded by the cylinder y squared plus z squared equal to 4 and the plane y equal to 2s minus 4 in the first octane. So again, we're looking for volume of a solid. Formula is volume of a solid. The formula is triple integral of number 1 over the solid region E. That's a formula for volume. Next, let's try to draw the solid region first. The solid region is bounded by the cylinder and the plane in the first octane. First octane is a region that x is greater or equal to 0, y is greater or equal to 0, and z is greater or equal to 0. That's the first octane. Let's draw the solid region first. This is a cylinder. For this cylinder, S component is missing. We only have y and z, So that's a cylinder parallel to the x-axis. That's a cylinder parallel to the x-axis. Since x component is missing, that's a cylinder parallel to the x-axis. And also, since we only draw a cylinder in the first arctan, it's a quarter of a cylinder. It's a quarter of a cylinder. And parallel to the x-axis. This is the cylinder. Y squared plus z squared equal to 4. That's a quarter of a cylinder. Next, we try to draw a plane y equal to 2x minus 4. This equation only contains x and y. So that's a plane perpendicular to the xy plane. That's a plane perpendicular to the xy plane and passing through the line y equal to 2x minus 4 in the xy plane. Let's draw this line in the xy plane first. For this line, if I substitute 0 for x, y is negative 4. If we substitute 0 for x, y is negative 4. If I substitute 0 for y, x is positive 2. Connect 2 points, I can make a line. Okay. So that's the plane. Y equal to 2x minus 4. Let me remove this unnecessary piece here. This is a plane. Y equal to 2x minus 4. If we observe this region, we can set out the integral in two ways. If we consider this is a type 1 solid, if we consider this is a type 1 solid, lower surface is the xy plane. Lower surface is the xy plane. Upper surface is this. Cylinder. So lower surface is xy plane, z equals 0. Upper surface is the cylinder. Y squared plus z squared equal to 4. If we get z by itself, z equal to positive radical 4 minus y squared. That's the upper surface. Integrand is 1. And we take double integral over region D. D is a projection in the xy plane, which is this trapezoid. Let me draw region D here. This trapezoid goes through 2 in the x-axis, goes through 2 in the y-axis. It goes through 2 in the x-axis, goes through 2 in the y-axis. And this piece here, when y is 2, if I substitute 2 for y, when y is 2, if I substitute 2 for y, we have 2 equal to 2x minus 4. So 6 equal to 2x, x must be 3. At this point, when y is 2, x must be 3. So this point is 3, 2, 0. This point is 3, 2, 0. So it goes through 3, 2 in the xy plane. Then connect 4 points, we can make trapezoid. This is region D in the xy plane. This is region D, this trapezoid in the xy plane. Then for this trapezoid, a better way to integrate is integrate from left to right. We can clearly tell this is left side curve, this is right side curve. Integrate from left to right. If we try to integrate from left to right, try to write x in terms of y. Try to write x in terms of y. Left side curve is s equal to 0. The right side curve is this line. If I try to get s by itself, y equal to 2x minus 4. If I try to get s by itself, y plus 4 equal to 2x. X will be half of y plus 2. X will be half of y plus 2. Right side curve is half of y plus 2. So x is from 0 to negative half of y plus 2. Y is from 0 to 2. Projection in the y-axis is from 0 to 2. If I push this entire graph into y-axis, projection to y-axis is from 0 to 2. Y is from 0 to 2. Z is from 0 to square root of 4 minus y squared 1 dz dx dy. You can try to solve this integral by yourself. It's very hard. If you have time, you can try to solve it. This integral is very hard. You can try to solve it. It's very hard to solve. It's very hard to solve this integral. So another way to solve this integral is, let's look at this region over. Can we find a better way to set out the integral? Let's look at the region over. Can we find a better way to set out the integral? If we treat this as a type 3 solid, we can see that that's the back surface. This is the back surface. That's the front surface. YZ plane is the back surface. This is the front surface. So for type 3 solid, if we treat this as a type 3 solid, for each solid, we try to write x in terms of y and z. For each surface, for the front surface and the back surface, we try to write x in terms of y and z. So try to write x in terms of y and z. This surface here is xz plane. Xz plane is s equal to 0. That's the back surface. The front surface, if we try to get s by itself, I can write s equal to half of y plus 2. If we try to get s by itself, I can write x is half of y plus 2. So if I set up the integral, the inner integral is x from the back surface to front surface. Back surface is s equal to 0. Front surface is s equal to half of y plus 2. Integral is y is 1 dx. Outer integral is the double integral over the projection d dA. Here, projection is this quarter circle. The projection is this quarter circle in the YZ plane. For type 3 solid, if I treat this as a type 3 solid, projection is this quarter circle in the YZ plane. Projection is this quarter circle in the YZ plane. Since D is a quarter circle, we can try to use polar coordinates in YZ plane. We can try to apply polar coordinates in YZ plane. So in YZ plane, Y represents X in SY plane. Z represents Y in SY plane. So we have Y equal to R cosine theta. Z equal to R sine theta. For D, if I apply polar coordinate for region D in the YZ plane, I treat Y as X in the SY plane. I treat Z as Y in the SY plane. So Y equal to R cosine theta, Z equal to R sine theta. Then substitute. Theta is from, it's in the first quadrant. Theta is from 0 to pi over 2. Radius is 1. Radius is 2. Sorry, y squared plus z squared equal to 4. Radius is 2. So r is from 0 to 2. S is from 0 to half of y plus 2. I can write y in terms of I and theta. Y is r cosine theta. Number 1, dx. And for polar coordinate, dA is always r, dr, d theta. I think this integral is easier than this integral. You can try. You can compare both. See which one is easier. I think this one is easier. Let's solve this integral. If we solve this integral, solve the inner integral first. Bring r inside first. Bring r inside first. Then solve the inner integral. Bring r inside first. R times 1 is r. dx, dr, d theta. Then we solve the inner integral. Theta is from 0 to pi over 2. R is from 0 to 2. Take antiderivative with respect to x. We have r times x. X from 0 to half of r cosine theta plus 2. dr, d theta. Then substitute upper and lower limit. If I substitute lower limit, I get 0. So all I need is substitute upper limit. Theta is from 0 to pi over 2. R is from 0 to 2. If I substitute the upper limit, I have half of r squared. We have r times half of r cosine theta plus 2 dr, d theta. Then distribute r. If I distribute r, we have half of r squared cosine theta plus 2r dr, d theta. Take antiderivative with respect to r. Take antiderivative with respect to r. Theta from 0 to pi over 2. R from 0 to 2. Take antiderivative with respect to r. I have 1 over 6 r cubed cosine theta plus r squared. One over 6 r cubed cosine theta plus r squared. Evaluate r from 0 to 2. If I substitute 0 for r, the entire integral is 0. If I substitute 2, I have integral theta from 0 to pi over 2. If we substitute 2 here, 2 cubed is a. A over 6 is 4 over 3. cosine theta. If I substitute 2 here, 2 squared is 4 d theta. Now this is a single integral. Take antiderivative with respect to theta. Take antiderivative with respect to theta. I have 4 over 3 sine theta plus 4 theta. Evaluate from 0 to pi over 2. If I substitute pi over 2, sine pi over 2 is 1. 4 times pi over 2 is 2 pi. If I substitute 0, I get 0. So the final answer is 4 over 3 plus 2 pi. That's the final answer.